In this video, we will discuss the postulates of Einstein and the Galilean transformation. This belongs to the lesson 1.1 in our learning guide and under the topic of the module of the special theory of relativity. In 1905, Albert Einstein published 4 papers of extraordinary importance. One of these is the analysis of Brownian motion. This is actually studying about the microscopic particle motion on the fluid. The next paper is we have the photoelectric effect, in which this paper Einstein awarded the Nobel Prize winner. Now the two papers which are the basis for the special theory of relativity, this is the paper wherein there is a drastic revision of the Newtonian concept of space and time. So, therefore, because of this paper, the Newtonian mechanics was already specified with a certain period of motion because of this paper. So, in this video, we will focus on the two postulates which are the basis for the special theory of relativity. Now, the first postulate of Einstein says that the laws of physics are the same in every inertial frame of reference. So, therefore, in describing motion, there might be a different answer for every inertial frame of reference. But all of them uses the same laws of physics. Now, when we say inertial frame of reference, this is a reference point, where it was assumed that the acceleration is 0. So, when we say 0, the velocity is constant, or it may be at rest. Now, usually, Earth is treated as the one of the reference, and that is the at rest position of that frame. There was also an observer which is moving, but it has a constant velocity. So, all of them uses the same laws of physics. So, suppose we have this activity wherein we have two observers, one observer on S frame, and we have another observer of the S prime frame of reference. These are all inertial. Stanley is the observer A, which is in the rest frame, which is usually Earth, and we have the Mavis, which is, we call this as the observer B, and this is riding on an inertial frame S, and within the moving vehicle we have this particle man. This is our subject for description of motion. So we have two observers, and these two observers uses an inertial frame of reference. This is at rest, which is Stanley, and we have the Mavis observer B in constant motion. Okay, so if this is moving, then the two observers A and B have different answer on the man on the moving car. So we have two descriptions of motion of the man. So what is the velocity of the man? Then there are two answers. One of that, according to Stanley, that the man moves with the same velocity of the moving vehicle or train. But according to Mavis, the man is not moving. It is at rest. So, the same question but different answers. Both of them are correct. Why? Because they use the laws of physics. Maybe says that the man is at rest because he didn't see any motion. But Stanley observed that the particle, the man, is moving with the same speed as the train. Now, aside from that, Mann and Mavis says also that Stanley is moving in opposite direction. So therefore, the Mavis and the Mann observed that Stanley is moving in the opposite direction. Okay, so what will happen if the man is moving within the train and the direction of the man is the same direction as the train? The question now is, what is the velocity of the man based on observer A, Stanley, and the observer B, Mavis? So how do you answer the problem? So suppose the train is moving at 150 kilometers per hour. This is measured from the rest frame. This is with respect to the Earth. So this 150 kilometers is the velocity from the reference of S prime or S observer A. While this 10 kilometers per hour, this is the speed of the man. And this is measured by Mavis. This is with respect to Mavis. The question now is, how much velocity acquired by the man? So, take note that according to Mavis, the man moves with 10 kilometers per hour. This is the velocity. M corresponds for the man, and this slash corresponds to with respect to S prime is the frame of reference of Mavis, and this is 10 kilometers per hour. This is the velocity of the man according to Mavis. But what is the velocity of the man according to Stanley? Is it the same as 10? The answer is no. It is more than 10. According to Stanley, the velocity of the man, this is M, with respect to slash, with respect to S prime or S, is equal to the velocity of the man with respect to S prime, which is happens to be 10 kilometers per hour, but it should be added by what? It should be added by the velocity of the moving frame or S prime with respect to S. And this is 150 kilometers per hour with respect to Earth. So this should be added by. Okay? So therefore, how much is the velocity of the man with respect to Earth? It should be 10 kilometers per hour plus 150 kilometers per hour. And the answer is 160 kilometers per hour. So according to Stanley, the velocity of the man is 160 kilometers per hour, but according to Mavis, this is only 10 kilometers per hour. Both of them are correct because they are of the same inertial frame of reference. They might have different answer, but they used with the same laws of physics. Okay? Now, what will happen if the direction of the man is in reverse direction? Suppose instead of having in the direction of the train, what if this man moves in opposite direction? So, what will be the answer? By the way, we call this as the relative velocity. The velocity is always relative to the observer, and that's the law. This is the first postulate of Einstein. Everything, the velocity is always relative to the observer, and the observer should have the inertial frame of reference. Okay, so if the man moves in reverse direction, so what will be the motion according to the two observers? So this is in opposite direction while speed of the train is 150 kilometers per hour. So for the S prime or the prime S, which is in the earth, and we have the S prime for the Mavis, according to Mavis, the velocity of the man is still 10 kilometers per hour but in opposite direction. So the same magnitude but the direction is reverse. This is according to Mavis. But what is the velocity according to Stanley? According to Stanley, the velocity of the man with respect to the S prime S is equal to the same formula. The velocity of the man with respect to Mavis or the moving frame plus the velocity of the train with respect to Earth. This should be the velocity of the man according to Stanley. So, substituting the values, this will becomes a negative. So, the man's velocity with respect to Mavis becomes a negative velocity. Why? Because this is in reverse direction. And this will be added by the same 150 kilometers per hour. And according to Stanley, the velocity of the man is 140 kilometers per hour. Okay? So, therefore, different observers have different answer because velocity is relative to the frame of reference. But they are both correct. Okay, so we will derive now the Galilean transformation equations before we're going to discuss the second postulate. The Galilean transformation uses the first postulate of Einstein. And this was also the basis of the first postulate of Einstein, the Galilean transformation. So, let us have the mathematical presentations of all the activities. So, suppose we have this S frame. S frame is a rest frame and we have the moving frame S prime. So, we have three dimensions. We have the X axis, Z axis, and the Y axis. And this is the origin, 0. Where in the S prime, or the moving frame, inertial frame, the horizontal, we have this as the X prime axis, and we have the Y prime axis, and this is the Z prime axis. And the origin is O prime, 0 prime, or the origin. And this is the moving frame at constant velocity. And this is the particle in the moving car. So how will you describe the position of the particle? What will be the position of the particle with respect to the observer in the rest frame or Stanley? Okay. Now take note that this is the man is assumed is moving towards along the x-axis. We have this velocity of this particle, and this is the description. This is the velocity according to frame S or S prime. Now, how much position of the particle with respect to Stanley? Okay. So this is the question. What is the position of the particle with respect to the rest frame? Now take note that the position of the particle with respect to S prime is X prime. So this is this position description of the S prime frame. So therefore, now take note that the distance from the rest frame of the distance of the moving frame from the inertial frame S frame is actually the distance. By the way, the speed of the frame is u. We will assign this. This is moving at a constant speed of u. So therefore, at zero time, this frame is start at the origin of frame S, but with respect to time, it was displaced because of this velocity. So for a given time, the displacement of S prime from S is actually the velocity times time, because the velocity times time is displacement. So mathematically, if you are solving for what is the displacement x of the man with respect to S, is simply as the S prime x prime added by the velocity times time, where u is the velocity of the moving frame and ut is the distance of the moving frame from the rest frame. So therefore, this is the one of the position transformation of Galilean. So if you are calculating the distance of the man from this reference, you have to add the position of the particle inside the moving frame, then added by the position of the moving frame from the rest frame. So it should be x prime plus ut, the position of the particle, moving particle. Okay, so differentiating this equation with respect to time, take note that the position with respect to time is velocity. So therefore, if you take the derivative of this with respect to t, the result becomes dx over dt. Dx means the infinitesimal displacement of the particle with respect to the S frame, while dx prime dt, this is the infinitesimal change of the position of the particle inside the moving frame. So we have dx prime over dt, and the derivative of ut is the dut over dt. Okay, so again, the change in position per time is velocity. So therefore, we can call this as the velocity. This is the velocity. By the way, this differentiating, this is with respect to time, so this is constant. So therefore, this, using our rules of differentiation, this is simply as u. And take note, u is the velocity of the moving frame, while dx prime over dt is our v prime, which means when we say v prime, this is the velocity of the moving frame, while v, this is the velocity according to the rest frame. The v prime is the velocity of the particle inside the moving frame. Adding the two, the answer is the velocity. This is the formula we used in our previous example. This is the velocity of the man, and this is the velocity of the train. So it should be added if this is moving with the same direction, but in opposite, you have to subtract it. So this is the position transformation with respect to x, and this is also the velocity transformation along the x-axis. Take note that in this motion, we assume that there is no displacement or position with respect to y and respect to z. So therefore, the motion is purely along x-axis. Okay? So we call this as the Galilean transformation equations, actually. So therefore, let us summarize. The Galilean transformation, the Galilean coordinate transformation are, we have along x, we have x prime. Suppose there is no, we will consider all the dimensions. So for x is equal to x prime plus ut. For y, there's no, in this case, there is no change. So there is, the y position is the same as the y prime position. So y is equal to y prime. Z also position is equal to z prime. So these are the coordinate, Galilean coordinate transformation. So take note that in inertial, the rest frame or the frame is, it has the coordinate of x, y, z. So x corresponds to the x-axis, y corresponds to the y-axis, and z is the z-axis. And this is the time. So While in the S prime, we have the x prime, y prime, z prime, and we have t prime. But in Galilean transformation, the time t in S is the same time in S prime. So they have different answer, but they have the same time of measuring the events of the two particles. So there's no difference with the time. This is the assumption of the Galilean transformation. So t, according to the observer in the rest frame, is the same as the time in the observer in the moving frame. Remember, the prime means it is a moving frame, while without prime, this is the observer in the rest frame. Now, the velocity transformation, Galilean velocity transformations are the Vx, this is the velocity component of the particle according to the rest frame, is equivalent to the velocity along x component of the velocity of the particle according to the moving frame, S prime, should be added by the velocity of the moving frame. U corresponds for the motion of the moving inertial frame. So with respect to y, since there's no change in y, so whatever velocity along y, the same as the velocity prime along y also. So the same velocity as z, so it differs only with along x. So if the problem is it has the component along x and component y, component along z, then this will becomes y prime plus u y t. So because this will be, the u becomes now divided into three components. Okay, so this will follow also for the z, and also with the velocities along y and velocity along z. But in this case, we assume that this is moving along x only. Okay, so let us apply this problem. Railroad flat car is traveling to the right. It's to the right at a speed of 13 meters per second. This is relative to the observer standing on the ground. So this is from Earth, and this is the observer. Someone is riding on a motorbike. So this is the flat car, and we have this motorbike. Now take note that this flat railroad, or the railroad flat car, this is moving 13 meters per second towards the right. And here comes the motorbike moving the same. Okay, it might be the same or in opposite. The question is, what is the velocity? Take note, magnitude and direction of the motorbike relative to the flat car. So the question is, how much velocity of this motorbike relative to the observer inside the moving frame? If the scooter's velocity, given the scooter's velocity relative to the ground, so relative to this person on the ground is given as 15, letter A, 15 meters, and the direction of the motor is to the right. Then letter B, the velocity of the motorbike relative to observer in Earth, and it is moving around towards left. So how much is the velocity according to the observer inside the car? And letter C, what will happen if this observer observe the motion of particle is at rest? So what are the answers to this problem? Okay, so take note that this is purely along x, so we can use the Vx is equal to Bx prime plus u, where Bx is what? This is the velocity of the particle with respect to the rest frame. The prime Bx prime is the velocity of the particle with respect to the moving inertial frame of reference, or S prime. And u is the velocity of the frame. Okay? So let's have the assumption that we'll assume that frame S is an earth. So call this as E. So this person is standing on the frame S. Then in S prime we have the flat car, and we have called this as FC, corresponds for the flat car. Then the particle of our target particle is the motor bike. Call this as M, corresponds for the particle. Okay, so therefore, what is Vx? Take note, Vx is what? This is the velocity of the particle with respect to Earth. So this will be the particle of the motor with respect to Earth. So M slash E. This should be equal to what? It should be equal to Vx prime. What is Vx prime? Vx prime is the velocity of the motor with respect to the flat car. So this should be velocity of the motor with respect to the flat car. So this should be plus. Take note, this is positive because we assume in our derivation that this is the same direction. So we have this positive. Okay? Then it should be added by u. What is u? Take note, u is the velocity of the flat car, and this is with respect to Earth. This is with respect to Earth. So what are the values? What are they given? In letter A, this is the target. This is the target problem. So we will solve the velocity of the motor. Take note, this motorbike with respect to the observer riding on the flat car. Okay, so this should be the velocity of the motor with respect to the flat car will be our target. So letter A, by the way, the velocity of the flat car with respect to Earth is given as 13. Okay, this is given the problem. And in letter A, you are given the 15 meters per second. This is the velocity of the scooter or the motor, okay, or the motor or the scooter, okay, motorbike, with respect to the ground. So this should be 15 meters per second, and this is the velocity of the motor with respect to Earth. E means Earth, so this is given as 15. So substituting these values, this velocity with respect of the motor with respect to Earth is 15, while the velocity of the flat car with respect to Earth is 13. So substitute everything, okay? This is 15 and this is 13. So we are now on the way to solve this target, which is the velocity of the motor or scooter with respect to the flat car. So transpose this one towards the left, then simplify. The answer is 2 meters per second. This is the velocity of what? The scooter or the motorbike with respect to the flat car, and the direction is towards the right. This is the answer for letter A. Letter B. In letter B, again, the same velocity of the flat car, but this time, again, the same question, what is the velocity and magnitude of the motorbike with respect to the flat car? If the scooter's velocity or the motorbike velocity relative to the observer on the ground is 4 meters. So, in letter B, take note, the only difference of this problem is this will becomes minus. Okay? Why? Because previously we used the positive because the direction is within the direction of the flat car. But this time it is in reverse, so this will be a negative. This should be a negative value. So this is our target. Now take note that the given is 4, and this is the velocity of the motor or the scooter with respect to Earth, and this is given 4 meters per second. So this will be substituted here. So it should be 4. Take note, this is minus, okay, as is, and this 13 velocity of the this is the velocity of the flat car with respect to Earth. Okay, so then this is the same as 13. So then transpose this to the left and this is to the right, then the result is 9 meter per second. The direction is towards left. That's the according to the problem. Okay, so this is the answer for letter B. This is much greater compared to the previous question, letter A. Letter A answers 2 meter per second, but this is 9. So when the motorbike reverses its direction, then according to the observer in the moving train, it is moving faster compared to the same direction. It's true, okay? It's true. It looks faster compared to, but according to the observer in Earth, his velocity is only 4 meter per second. But according to observer in moving train, it's 9 meter per second. Now, what will happen if the observer in Earth, in letter C, says that the motorbike is at rest? So, what will be the velocity according to the observer inside? Okay, that will be our question. So, okay, this is, we will assume this is positive because this is at rest. Okay, we will use the same the formula. This is a formula. Then, but the difference is the velocity of the particle or the motor or the scooter with respect to Earth is 0 now. So this is 0, and this is still the same as 13 meters per second. So substitute the values, transpose. The answer is negative. So what's the meaning of negative? The negative means the scooter moves towards the left with the same velocity. So the black car moving towards right and the motorbike is moving towards left with the same magnitude. So observer on Earth says that this is at rest. The motorbike is at rest. But according to observer inside the train, the motorbike moves 13 meters per second in opposite direction in the motion of the flat car. So these are the answers to the problems A, B, and C. Okay? Now in the second postulate, according to Einstein, the speed of light in the vacuum is the same in all inertial frames of reference. Okay, what does it mean? And take note, it is independent to the motion of the source. So when we see light, speed of light, whatever motion or whatever answer of the observer A and observer B must be the same. Why? Because it is independent to the motion. Whether it is moving to the left or moving to the right, the answer is always the speed of light. This is the second postulate of Einstein. What is the meaning of that? So therefore, we cannot apply the Galilean transformation in this case. Why? Because the Galilean uses the two observers, and the two observers have different answer for the particle moving. Now, if we change the particle moving, instead of man, we will replace that with a light. So the question now is the Galilean transformation applicable if the particle is light particle? So the answer is no. Why? Because according to, we cannot use the Galilean, because according to this second postulate of Einstein, the speed of light in a vacuum is the same. So therefore, the speed of light does not change even if the frames are rest or moving frame. And take note, this is independent to the motion of the source. So replacing, instead of having man, let us say this is moving towards the direction of the car or the frame, moving frame. But take note that we have the speed of light. The speed of light is c. Okay, so the speed of light is c. C is it has a value of 3 times 10 raised to 8 meters per second. So we replace the moving man with the source of light. So the light now travels towards direction. So the question now is, what's the velocity of light according to Mavis and according to Stanley? Okay? So if you use the Galilean, take note, this is 3 times 10 raised to 8 meters. This is the speed of light. Now, if we use the Galilean, so this will be the result. C plus EU. EU is 150 kilometers per hour. So therefore, the speed of light particle now is C added by 150. Okay? Now, according to second postulate, this is not true. This is actually not included because Stanley says that the speed of light is C, and also with Mavis the same. Speed of light does not depend on the medium and does not depend on the source. Okay? Now, this is the second postulate. So therefore, the second postulate immediately implies that the following results. It is impossible for an observer to travel at sea. So therefore, no one can move, no particle can move with the speed of light. Okay? So the ultimate speed is only what? Is only the velocity of light. Particles cannot move more than the speed of light. Okay? So the question is, what is the basis of Einstein to have this second postulate? Now, according to the book, in 18th century, physicists believed that the light travels through the hypothetical medium called ether. This is the perspective of the physicists during this time, in 19th century, like the Maxwell, okay, and other physicists believes that the light move with respect to the medium ether. So there must be something, but ether is an hypothetical. So this is not yet observed, but they have the conclusion that the light moves with respect to ether. Just like sound travels through air, so light should travel with respect to ether. But Michelson and Morley experiment in 1897 before, okay, they are trying to observe, to detect the motion of the light. They want to verify the existence of the ether. Okay, but they were able to detect no ether motion across the earth, and the ether concept has been discarded. So this experiment, they thought that the experiment is failure. No, there is no result because their objective is to verify the ether. But Einstein says that they were not able to find the ether because ether does not exist there, because light doesn't depend on the medium. So this is actually the basis of Einstein, why he provided this second postulate, wherein the speed of light in a vacuum is the same in all inertial frame of reference. So therefore, all observer in the frame of reference must provide an answer of 3 times 10 raised to 8. And this is the second postulate. So the question is, how will we use this one? This is actually, the second postulate will be used in the next topic, in the lesson 1.1.2, in the time dilation, then going to the time length of contraction, and until we will revise the formula for Newton's law, the momentum. Okay, so this is the basis of the special theory of relativity. When the particle is moving towards the speed of light, there must be a relativistic activity. This will be our next topic. Okay, so Thank you for listening.